Okay, well, let's go ahead and get started then. 9:10. Um, so we're back talking about perturbation theory, and just a reminder that last time we talked about a few different things. First of all, we just talked about perturbation theory for algebraic equations. And so, for instance, if we have, a quadratic like this, there's a couple ways that we can handle solving that, right? Of course, a quadratic, you could just solve it using the quadratic formula, but we use the fact that we had a full solution to demonstrate a couple of different methods. One is the iterative method, where you reformulate the problem as a discrete map, essentially, where you map one guess to another through an update equation that satisfies the original algebraic equation. And in doing that, you've created a discrete dynamical system whose fixed point actually is going to be a root of your original equation. The other approach we looked at is the expansion method. And essentially, in this case, you assume that x takes the form x0 plus epsilon x1 plus epsilon squared x2, and so on. Plug it in, equate powers of epsilon, and solve up the hierarchy of epsilon powers. This works if this is the correct expansion, but it may not necessarily be the correct expansion. First of all, you may not necessarily be able to start at order 1. And in the case of singular perturbations, as we introduced last time, you'll recall that if you have a term, let's say, that vanishes, the highest power term vanishes as epsilon goes to 0, then you're going to have a qualitatively different equation at epsilon 0 as opposed to small epsilon. And so actually you're going to have one of your roots vanish once you set epsilon to 0. And so it's going to be, you have to take a different approach essentially to perturb around that. Fortunately, in this case, what we found is that to get the singular root, you essentially take x equal to some scaling of 1 over epsilon. And in this case, it was just 1 over epsilon. And all the other terms are essentially as before after that. Okay. Now, we work this out just assuming the particular form of the expansion. You might not know that, though, and you may need to figure this out based on your problem. Okay, so there's a couple ways to do this. Okay, one way is what's called rescaling. Okay, and rescaling essentially for singular problems, okay, can essentially de-singularize, essentially remove the singularity by rescaling some variables. Okay, it means you just turn it into a non-singular problem. So in the case of our canonical singular problem, this just quadratic equation, we could take some new variable, big X, which is equal to epsilon times little x, okay? So little x is equal to big X divided by epsilon. So if we plug this in, what do we get? We get epsilon big X divided by epsilon squared plus big X divided by epsilon minus 1 equals 0, okay? What has this bought us in this case? Well, if we multiply by epsilon and we simplify, what we get is big X plus X minus epsilon equals 0. The epsilon no longer lives on the highest order term in this case, so we no longer have a singularity. So what we could do in this case is then just solve this as a regular perturbation problem, okay? So of course, what I had to do was pick some sort of rescaling. Again, you may not necessarily know how to do this, right? And you'll notice that when epsilon is 0 here, you're going to have two roots. One will be big X is minus 1. The other will be big X is 0. So the non-singular root is still going to have a sort of a standard regular perturbation expansion. The singular root now is going to involve this 1 over epsilon term, as we found before. Okay, so so it's important to note, okay, that you must be able to pick a helpful rescaling, okay? Now, in practice, you can do this sort of by guessing, right? So you could say, well, let's try divided by epsilon, epsilon squared, epsilon 1/2, you know. If this is your research area and you do it a lot, you may eventually be able to gain some intuition for doing this, okay? But let's maybe talk about a more systematic way of thinking about this, of finding a rescaling, okay? Questions so far before I move on to that? Okay. So how do we find rescaling? Okay. And I'll talk about that in the context of this example, but essentially the systematic approach we can describe as follows. Okay. That you're going to pose a general rescaling, okay? And this is going to have some factor, delta of epsilon in this case, right? So you don't necessarily know what that is ahead of time. Little x equals delta of epsilon, some function of epsilon times big X. Before it was one, you know, delta of epsilon was 1 over epsilon. It doesn't necessarily have to be. And then X is your new variable that's going to be of order 1. That's big O of 1 as epsilon goes to 0. Okay. So for example, right, let's return to our original example of a singular problem. We have epsilon delta squared, x squared plus delta x minus 1 equals 0. And let's just consider what's called the dominant balance as the size of delta is varied. Okay, dominant balance just means the leading order sort of balance terms. Okay, so there's a few situations, right? You could pick delta of epsilon to be much less than 1, right? If it was very small, then what would happen? And I won't get too specific, but we can sort of say things are either, you know, small, order 1, or large. okay? So in this case, if delta is small, delta squared is going to be very small, times epsilon is going to be very, very small, delta is going to be small, and then 1 will just be order 1. So we have small plus small minus 1, okay? Now the problem is this needs to equal 0. So the equation we get to leading order is going to be minus 1 equals 0. So that means we can't balance the 0, okay, on right-hand side. So probably not the type of rescaling to use. So this means we can essentially rule out taking delta of epsilon being small. We already know the answer, delta of epsilon to take, because I showed it before. This is showing how we can arrive at that sort of systematically, okay? Next approach is that we essentially do nothing and we take delta equals 1, okay? Now we know that this is probably not going to work, but let's just see what we get when we look at delta equals 1. Well, in this case, right, our quadratic ends up giving us something small, okay, plus x minus 1, okay, and that needs to equal 0, okay? Now, it works for getting us our non-singular root, right? It produces the regular root, because to leading order, we can take x equals 1, and we get 1 minus 1 equals 0, everything's fine, okay? So the regular root now, x equals plus 1 minus something small, right? But this is not the singular root, okay? So this guides us to the fact that we probably need to take delta to be large, right? But how large should we take it? Let's break that down into 3 cases, okay? So let's say, for instance, we try delta is something between 1 and order epsilon to the minus 1. So this might mean that we want to take, delta to be negative fractional power, right? So in this case, the delta x term dominates, right? Because we have the typo before. Now let me just fix a quick typo here. So this here, this should not have a squared on it. Sorry about that. Okay. No squared power here. Sorry, that was just a minor typo. Okay. All right. So now let's look at this, right? So if we take delta to be between 1 and epsilon to the minus 1, right? Delta x is going to dominate, right? Because this term is going to be smaller than this term. Another typo. Sorry about that. I don't know where I'm getting all these extra squareds. Okay. All right. So, right. So this term, right, is going to end up being bigger than this term here. Okay. So delta x dominates. Let's just rescale the equation. We get epsilon delta squared x squared plus delta x minus 1. We'll divide it by delta, okay? And this is going to equal to what, okay? Well, this is smaller than epsilon, so, or it's smaller than epsilon to the minus 1, right? So epsilon times delta squared divided by delta is still going to be small, okay? This middle term is just going to be x, and then we get minus 1 over delta, which is much bigger than 1. So that term is going to be small, okay? Equal to 0. So this implies that that will balance the 0 on the right-hand side if x is equal to 0, okay? But this is going to violate our assumption that x is of order 1, okay? So that kind of rescaling won't work, okay? So we've eliminated possible rescalings. Now we know that delta either needs to be 1 over epsilon or something of order bigger than that, right? So we're almost there, right? Again, you know what the answer is going to be, but this is just showing you the steps that you could take to get there if you didn't sort of know it ahead of time. Now let's take delta is epsilon to the minus 1. In this case, we get let's say that if we want to rescale the equation by epsilon delta squared, right? We end up with x squared. And then we also know that epsilon delta squared is then just going to be delta itself, so that'll cancel this term. So we get x squared plus x minus something small, okay? And this is going to balance the 0 on right-hand side, okay? And gives the singular root, right? X is equal to minus 1 plus something small, okay? So we have something non-trivial for the leading order term of x. That's order 1. And then we know that there's some trailing smaller terms after it, okay? So this then is the rescaling that we want to use, and it is the one that we pointed out before, right? Let's just look at what would have happened, finally, if we'd have taken delta to be epsilon to the minus 1, okay? In that case, you have epsilon delta squared, x squared, plus delta x minus 1 divided by epsilon delta squared, okay? This is going to be equal to x squared plus something small minus something small, okay? And the first term dominates, okay? And again, x equals 0, and this violates our x is order 1 assumption, okay? All right, so you can kind of see how to build this up systematically. You could do it with a lot more granularity, right? You could take, you know, let's try epsilon, delta equals epsilon to the 1/2. Let's try delta equals epsilon to the minus 1/2, and so on, right? If those sort of more standard rescalings aren't working, you might think about trying something like an iterative method. But that can be difficult also because if you don't necessarily know where to start, then you won't maybe arrive at the correct root. Remember, there's 2 roots in this case, and the much harder one to get, or the one that requires more work, is the singular root, right? So it can help to plot what happens to the roots as functions as epsilon goes to 0. Sometimes you need to be initially guided by numerical results before you can get some sort of analytical results. All of those things may go into helping you finding a rescaling, okay? But this sort of systematic approach, it can often work well as long as you have sort of a more standard rescaling that would work, okay? Questions about this, about rescaling or this approach? Okay. All right. I will briefly mention an alternative method. And that's this, that you just compare terms pairwise, okay? What do I mean by this? Essentially that within your equation, you want to balance at least two terms, okay? And we call this sometimes the distinguished limit, okay? And this can be quicker than the systematic approach of sort of exhaustively trying different rescalings. So in the case of our problem, right, we might try and just balance the first and the second terms, okay? What do I mean by this? I mean, like, you know, look at the first and second terms are epsilon x squared x, right? So this must mean that I need to take x is equal to something order epsilon to the minus one, okay? And this would get me the singular root, okay? This will often work when maybe the systematic approach doesn't work or it's just taking forever, right? I look at two terms in my equation and I say, let's have those be the same order. In that case, what does my unknown variable have to scale like in order to match those terms up? In this case, x needs to be of order epsilon to the minus one, okay? That would give me the singular root. If I balance, on the other hand, the first and the third terms, okay, that would mean looking at epsilon x squared and minus one. So I might try taking x to be order epsilon to the minus one half, okay? It turns out that this makes both terms order one, okay? But the leftover term, which is x, then needs to equal order epsilon to the minus one half. And there's essentially no way to balance that term, okay? So that won't work because you have a stray term that can't be balanced unless you take it to be zero, okay? Which sort of defeats the purpose of naming your scaling, okay? Third case is balance your second and third terms, okay? And in this case, we would have x and minus one, right? So x is just going to be order one. And as we found before, this leads to our regular root, okay? So another approach, usually quicker, may be best one to try in situations where you don't have that many sort of combinations to check, only sort of 3 combinations to check in this case. All right. Okay. So the next thing I want to talk about, and I sort of alluded to this before, is what if you're looking for a perturbation expansion and integral powers of epsilon are not working, okay? What do I mean by this? Well, I just mean, let's consider sort of perturbation expansions that involve fractional powers, okay, in epsilon. So for instance, let's look at the following algebraic equation. Again, it's quadratic, so we could just, you know, solve it using quadratic formula. But I want to note something that is interesting and maybe gives us some insight into when we may have to deal with these fractional powers, right? At epsilon equals 0, right, you would just have x squared minus 2x plus 1 equals 0. What are the roots of that equation? What's the roots of the epsilon equals 0 equation in this case?
1.
Yeah, just 1 and 1, right? So it's double roots. X equals 1 is a double root, okay? And this implies, right, that, you know, this is not necessarily a singular problem, okay? but you may run into some possible issue because you need to basically take this double root, right, and turn it into two different roots for epsilon is greater than 0. Okay. So let's just try the naive approach of the regular perturbation expansion. And this is not a bad idea when you're doing asymptotics. You may as well just always try the regular perturbation expansion first, unless you have cause to, think that it is not going to work. Okay. So let's see what happens. If I try the expansion method, right? Regular perturbation expansion, I substitute this in. I have 1 minus epsilon 1 plus epsilon x1 plus epsilon squared x2 and so on squared, okay, minus 2 1 plus epsilon x1 plus epsilon squared x2, so on, right, plus 1 equals 0. Now let's expand, okay. In this case, I'm going to get 1 plus 2x1 epsilon plus 2x2 plus x1 squared epsilon squared plus dot dot dot. Okay, that's for my squared terms, right? Now my my epsilon term. So this is sort of 1 times all this. The minus epsilon times all this gives me minus epsilon minus 2x1 epsilon squared, okay, plus dot 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 dot, skipping down to the next line. Now I'll expand this term here. So you're going to minus 2 minus 2x1 epsilon minus 2x2 epsilon squared plus dot dot dot, okay, plus 1 equals 0. Okay, so this is all the stuff that comes from 1 times this. This is the stuff that comes from minus epsilon times this. This is minus 2 times that linear term, and then I have the plus 1 trailing on the end. Okay, so now I have this long expansion, endless of terms, right? I'm going to match powers, and we start at epsilon to the 0, right? I have 1 here, I have a minus 2 here, and I have a plus 1 here. So far, all is well because that agrees, right? But at epsilon to the 1, what happens? I get 2x1, right? Then I look over here, I have a minus 1 times epsilon. And then I have, sorry, I left an epsilon out of there. I have a minus 2x1 from this term here, right? Okay, so this is supposed to equal 0. And if I simplify, I get minus 1 equals 0. Okay, that doesn't work. Okay, so the question is, what went wrong? Okay, well, the answer is I just took an expansion that doesn't work. I took an expansion that skips a term that I need in my asymptotic expansion. Okay, so let's see how I can find that, right? Now, note, in this problem, again, I can sort of make it easy on myself, and I can find an exact solution to give me some insights here, okay? But again, the insights that we glean from this, we can then sort of apply to other problems, right? And again, the double root should be a clue that I'm going to maybe have to take a non-regular expansion, right? Or sort of a non-standard expansion, okay? So this is my root that I would get from applying the quadratic formula. And if I expand it, right, using like binomial series, I get 1 plus epsilon to the 1/2 plus epsilon to the 3/2 and so on. So I need an expansion that involves fractional powers of the 1/2. Okay. So we needed powers of epsilon to the 1/2 in our expansion. Okay. And so maybe sort of some hand wavy insight into this is that we are perturbing about a quadratic function's minimum, right? So here's our function, right? And there's our root there, right? X equals 1, okay? And just note that, you know, any sort of small perturbation to this equation, okay, is going to sort of shift this up and down, right, to create now 2 roots, okay? And it's not necessarily going to be the same thing that happens if we were to just shift something that's more linear up and down, right? So small changes to this equation, right, are going to have sort of order epsilon to the 1/2 changes in our roots, okay? So now we're going to try then this expansion, right? X equals 1 plus epsilon to the 1/2 x1 plus epsilon x2 plus epsilon to the 3/2 x3, right, and so on. And if we substitute this in to our equation, we get 1 minus epsilon plus epsilon to the 1/2 x1 plus epsilon x2, and so on, that's squared, minus 2 times 1 plus epsilon to the 1/2 x1 plus epsilon x2, and so on, plus 1 equals 0, okay? So that by expanding, okay, I'm now going to have to expand in powers of epsilon to the 1/2. I'm going to have to collect each of those terms up the hierarchy, okay? So my expansion now gives me 1 plus 2x1 epsilon to the 1/2. This is the 1 times this quadratic term here, plus 2x2 plus x1 squared epsilon plus 2x3 plus 2x1 x2 times epsilon to the 3/2. Now we have the minus epsilon times all those terms, which is minus epsilon minus 2x1 epsilon to the 3/2 plus, now I write it minus 2 minus 2x1 epsilon to the 1/2 minus 2x2 epsilon minus 2x3 epsilon to the 3/2 plus 1, and this is equal to 0, right? So stuff from the quadratic term times 1, stuff from the quadratic term times minus epsilon, stuff from the linear term, and then it's just plus 1 equals 0. Now, the next step always is to match powers and solve those algebraic equations, okay? What does that look like, okay? Well, we should expect that matching powers at epsilon to the 0 shouldn't look much different, right? Because the leading order terms are all the same, right? So we still get 1 minus 2 plus 1 is equal to 0. So that's fine. But now at epsilon to the 1/2, epsilon to the 1/2, we get 2x1 minus 2x1 equals 0, okay? And that works basically for any x1, okay? But now, okay, I'm just gonna to try and have this all on one page now. At epsilon to the 1, right, I end up with 2x2 plus x1 squared minus 1 plus 2x2 is equal to 0. This implies that x1 squared is equal to 1. So that implies that x1 is equal to plus or minus 1. Okay. So I get the two roots that branch off, okay, from the double root there. Okay, so I get two distinct roots basically as I change epsilon in this case. All right. So that's my next order up term. And now at epsilon to the 3/2, I get 2x3 plus 2x1 x2 minus 2x1 minus 2x3 is equal to 0. This implies, just when I cancel everything out, right, that x2 is equal to 1, okay? So what I have is x is equal to 1 plus or minus epsilon to the 1/2 plus epsilon plus so on and so on, right? And typically, you're not going to expand up to, like 7 terms or something like that. There are a lot of reasons for that. Usually you just want to keep the first 2, 3, 4 terms or something like that. Okay. So that's the idea with fractional powers. Now, again, how would you know the expansion that you need to use, right? So you can do this through term matching, essentially. You can say, well, I know what happens at order 1, okay? To get a sense of what my expansion should be, let me look at how I can sort of match up terms at next order, okay? So you can essentially try an expansion that's 1 plus epsilon, to the p times x1, and then sort of figure out what that p should be, okay? So to figure out in general what fractional power to use, okay? Basically, phi x equals x0 plus epsilon to the p, okay, x1, and so on, and see what power p gives basically admissible next order equations, okay? So you can tune this p basically, and then your next order up would be e to the 2p, e to the 3p, and so on, okay? All right, questions about this? Okay, so that's fractional powers, right?
Zach, I have a question.
Yeah,
So when we tried to do it, and it failed because we couldn't match terms up, that happened relatively quickly. Could it be the case that we needed to choose epsilon to some power, but didn't know that and tried to match terms and didn't go far enough in the series to realize that it would fail?
that could happen, right? But you still may have a decent expansion though, at lower order in that case, right? I mean, there are, there's not necessarily a always a unique way to sort of do an expansion, right? Especially because you could have multiple roots. And so, yeah, I mean, as you'll find, that kind of thing can happen, but it may be that you still get sort of a good enough expansion that way, right? Yeah, but you're skipping terms. the thing is that expansion will sort of break down sooner than the order epsilon 1/2 expansion in that case. But yeah. Okay. All right. So I gave sort of a hand wavy argument about how to find the right expansion. Let's dig a bit deeper, right? And say if we wanted to do it a bit more systematically, okay? So the idea is if we did not know, okay, which expansion to choose, okay? The idea in general, right, is that we could pick x equals 1 plus delta 1 times x1, okay? Just calling it delta 1 because I'm pairing it up with x1, right? So the idea is that we then sub this into our equation, and we end up with 1 minus epsilon, 1 plus delta 1, x1 squared minus 2 times 1 plus x1 delta 1 plus 1 equals 0. Expand, right? 1 plus 2 delta 1 x1 plus delta 1 squared x1 squared minus epsilon minus 2 epsilon delta 1 x1 minus delta 1 squared epsilon x1 squared minus 2 delta 1 x1 plus 1 equals 0. Okay. Now let's simplify this, right? Delta 1 squared x1 squared minus epsilon minus 2 epsilon delta 1 x1 minus delta 1 squared epsilon x1 squared equals 0. Okay, so all the kind of order 1 terms vanished, right? And we're just left with sort of this term matching problem where we can tune delta 1, right? You know, up here I said that should be epsilon to the p, but you know, in general, this could be something even beyond you know, fractional powers, right? You can extend this method to beyond just fractional powers in epsilon. Okay. So the idea here is sort of like what we were talking about in the case of singular perturbations, right? That we want to find the dominant balance. Okay, how do we pick delta so that the leading order terms match up? Okay, well, leading order terms are delta 1 squared x1 squared and epsilon, right? Because right, this is going to be higher order, right? And we'll assume that delta 1 needs to be something between 0 and epsilon in this case. Okay, so essentially, since epsilon delta 1 is going to be much less than epsilon. Okay, so here's our leading order terms. Okay, and so we find delta 1 by just saying, let's match our leading order terms. That tells us that delta 1, right, squared needs to have the same order as epsilon. So that immediately tells us that delta 1 needs to be epsilon to the 1/2. Okay. So just to say that in words, thus delta 1 squared must balance epsilon. Okay. And so that implies that delta 1 is equal to epsilon to the 1/2. Okay. Therefore, okay, taking our equation from before, x1 squared minus 0, minus 1 equals 0. Therefore, x1 equals plus or minus 1, as we found before when we used the epsilon to the 1/2 expansion. Okay. Now at higher order, you can just do this again, right? at higher order, you don't have to necessarily say that at next order, the term is going to be epsilon to the 1/2 squared, which would be epsilon, right? You could leave it much more general, right? So you could try x equals 1 plus epsilon to the 1/2 plus delta 2 x2, okay? And we know that delta 2 now needs to be much less than epsilon to the 1/2 to be sort of the next term in the expansion. If we sub this in, then we get 1 minus epsilon times 1 plus epsilon to the 1/2 plus delta 2 x2 squared minus 2 times 1 plus epsilon to the 1/2 plus delta 2 x2 plus 1 equals 0. Expand, as we always do with the expansion method, 1 plus 2 epsilon to the 1/2 plus epsilon plus 2 d2 delta 2 x2 plus 2 epsilon to the 1/2 delta 2 x2 plus delta 2 squared x2 squared minus now our times epsilon terms minus epsilon 2 epsilon to the 3/2 minus epsilon squared minus 2 epsilon delta 2 x2 minus 2 epsilon to the 3/2 delta 2 x2 minus epsilon delta 2 squared x2 squared minus 2 epsilon to the 1/2, okay, minus 2 delta 2 x2 plus 1 equals 0. Okay, I'll write this all out because in practice, you're going to have to go through a lot of these expansions. Very easy to make errors, by the way. So, find a way that works. Maybe need a large sheet of paper sometimes to do these calculations. Okay. If I simplify this, right, we get the following: 2 epsilon to the 1/2 delta 2 x2 plus delta 2 squared x2 squared minus 2 epsilon to the 3/2 minus epsilon squared minus 2 epsilon delta 2 x2 minus 2 epsilon to the 3/2 delta 2 x2 minus epsilon delta 2 squared x2 squared equals 0. Okay, now let's look at this equation. In particular, since delta 2 has to be a lot less than epsilon to the 1/2, okay, the dominant term involving delta 2 is 2 epsilon to the 1/2 delta 2 x2, okay? And this must balance, okay, minus 2 epsilon to the 3/2. So delta 2 is equal to epsilon, and we get that x2 is equal to 1, okay? So just to look back at this, right? This even simplified, this looks like there's a lot going on here. But this is a delta 2 squared, so we know that's going to be smaller, okay? This is a larger term than this, right? Epsilon times delta 2 is smaller than this. Epsilon to the 3/2 is smaller than this. Epsilon times delta 2 squared, okay, is going to be smaller than this. So we know that this is the term to zero in on, and this is the other term to zero in on. So again, with these perturbation expansions, it's about finding these leading order terms and saying, how can I equate these terms, okay? And whether that's about scaling or just, sort of power matching in order to get your expansion in this case, okay? So again, in this case, we get the same expansion that we got before, right? Which is going to be, and I'll just write it up here, just so I don't have to grab another page, right? x equals 1 plus epsilon to the 1/2 plus epsilon plus yada, yada, yada. Okay. I think we're at time for today. Let me just recap what we did. We looked at doing rescalings in order to handle singular equations. There's two ways to do that. One is you can march through all the possible rescalings and find the one that works best. The other way is to just look at all the terms in your equation and figure out which two terms you want to match and what happens when you do that. For expansions with non-integral powers, you can either sort of guess these based on experience and intuition, but if you want to find the right expansion, okay, a much more systematic way of doing this is that at each step, figure out the scaling that works for the sort of next order term in your perturbation expansion. Okay. Questions about this so far?
So when we decide that we need to have some like fractional term, are we saying something about the kind of singularity, like this is a branch point with two branches, or you know something like that?
Yeah, you'll find that equations of sort of similar class are going to end up giving you similar sort of fractional power expansions. So that was my point about the quadratic nonlinearity creating that double root, okay? Because of the way that the quadratic function grows away from that double root, that's why you get a 1/2, right? If it was a cubic or a quartic nonlinearity, you might expect, fractional powers of a third or a fourth or something like that. So at that level, you can use those sort of insights, and that can help you if you sort of see that kind of problem again. And certainly, applied mathematicians sort of use that information. But to your question from before, you can sometimes find an expansion that works. It gives you the first few terms. It works okay. People may even publish a paper, get it accepted on that. And then at a later date, somebody says, no, I found a better, more accurate expansion. So that's the curiosity and sort of the exciting thing about asymptotics is that, it's hard to, prove for sure this is the absolute best, asymptotic expansion. But, for simple cases, they're worked out enough that you can often do that. So. Okay. Other questions? No, I'm a bit over time. Okay. Cool. Well, I'll upload this to the cloud, just like I did the other one or YouTube as before. Yeah, remember that homework's due a week from Friday. Again, I would encourage you to get started on that if you haven't already. There's no more scheduled office hours this week, but if you want to shoot me an email, if you want to ask me some questions as you're working on the homework or circle back about the lectures, just send me an email and we can set up a Zoom time. So otherwise, see you on Friday.
Thanks, Zach.
Thanks.